All right. We're going to move on to Chapter 4 now. We're going to talk about energy. Energy is the capacity to do work. There's two types of energy: potential energy, which is stored energy, and kinetic energy, which is the energy of motion. If you had a bigger book, make it bigger. So if you look at a dam, the water behind it is potential energy. If the dam breaks, you're going to see a lot of kinetic energy. At least until the water hits you, you'll see a lot of kinetic energy. And you'll feel a lot of kinetic energy. Okay? The law of conservation of energy says the total energy in the system doesn't change. Energy cannot be created or destroyed. So if you think of the universe as our system, all the energy that there is, and ever will be, has been there from the beginning. We don't create energy, we don't destroy it, we merely change its forms. And you can think of, we turn electrical energy into mechanical energy. You know, a hydroelectric dam turns mechanical energy, the rushing of water, into electrical energy. And the same thing happens in chemistry. We have chemical energy that gets transferred to mechanical energy, and vice versa. So what about units of energy? We have what's called a calorie. It's the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So if I have a milliliter of water, which is 1 gram, because water's density is 1 gram per milliliter, and I heat it from 24 degrees Celsius to 25 degrees Celsius, I've expended 1 calorie of energy. Another unit that's used in chemistry is called the joule, capital J. 1 calorie is equal to 4.184 joules. So that's something we'll be using during the semester for energy, joules. And of course, there's the kilojoule and the kilocalorie, where 1,000 calories is 1 kilocalorie, and 1,000 joules is 1 kilojoule. So whereas 1 calorie is 4.184 joules, 1 kilocalorie is 4.184 kilojoules. Okay? Still copying? You know, I have these are on the PowerPoints. These are the PowerPoints. Okay. What about the nutritional calorie? You notice that is a capital C. We call them large calories in some cases, or nutritional calories. They're equal to 1,000 small calories. So when you have your breakfast bar or your Snickers bar, and it says 250 calories, those are the big calories. Those are equivalent to 250,000 little calories. Why, if you eat that Snickers bar and you say, well, I'm just going to jump on the treadmill and use up all those calories, you end up on that treadmill for like 30 to 40 minutes. Because you got to burn 250,000 little calories. When we eat, the process of breaking down the food is called metabolism. Proteins, carbohydrates, and fats release a predictable amount of energy. It's called the caloric value. So, proteins contain 4 nutritional calories per gram. Carbohydrates contain 4 nutritional calories per gram. Fat contains 9 nutritional calories per gram. So fat really has more energy per gram than proteins and carbohydrates. So, if we're going to eat a baked potato, it contains 3 grams of protein, a trace of fat, 23 grams of carbohydrates. Estimate its number of calories, nutritional calories. Well, we have 3 grams of protein, 23 grams of carbohydrates. If we look at 1 gram of protein is 4 calories, and we have 3 grams. So we have 3 grams of protein times 4 calories per gram. So we have 12 calories from the protein. 23 grams of carbohydrates times 4 calories per gram is 92 calories from the carbohydrates, for a total of problems with the pen. Try pen again. 104 calories. So there isn't a lot of calories in a baked potato. That is a plain baked potato. Once you put the sour cream, the cheese, the bacon bits, and everything else, all that goes right out the window. But if you just eat a plain baked potato, anybody here eat plain baked potatoes? One person. I mean, I don't understand how you can do that. I mean, you got to put the butter on it, the other stuff. So roughly 100 calories for a baked potato. I noticed they rounded down from 104. This must be from some diet book. So we can go through and look at food values and figure out where the calories come from. You can look and see how much protein, how much carbohydrates, how much fat are in the foods, and you can estimate how many calories are in there. So we're going to kind of switch gears a little bit here. And we're going to start talking about the 3 states of matter as related to energy, specifically kinetic energy, energy of motion. If we look at a gas, the kinetic energy is high. The particles are moving quickly, and they're far apart. So the attractive forces between molecules are negligible, allowing them to move freely. So it's just like if you leave this class today and you go out this exit, and you're going over to the health building, and someone's coming out the back of the health building that's going to come the other way, and you're both running to your next class, and you see your friend, you may get to wave briefly at them, but you don't have any interaction. You're far apart, you're on opposite sides of the building, and you're moving quickly. With a liquid, the attractive forces hold the molecules much more closely. Distance between the molecules and the kinetic energy is much less. So you can think of that sort of like if you've ever been on a subway, either like in Washington or New York, during rush hour, the train stops, the doors open, 800,000 people come out, 800,000 people go in, you're close to each other, but you're still moving because you want to get on, they want to get off, so you kind of slide past each other. Okay? So that would be like a liquid. And you can only move so fast because of the crowd. Solid, on the other hand, the attractive forces between the molecules are much stronger. The distance between the particles is small and there's little freedom of motion. You can think of that like getting on an elevator that has a capacity of 15 people, and you're the 21st person to get on there. Okay, so you're like stuck, like proverbial sardines in a can. You can't move one way or the other. Okay, you can maybe do something with your hands. But you're very close together. There's absolutely no motion. So a gas expands to fill its container. So someone drops a bottle of perfume in the back. Eventually, we'll smell it up here in the front. And if the door's open, eventually they'll smell it out in the hallway because the gas just keeps expanding, diffusing, dissipating. A liquid has a fixed volume that takes the shape of the container. So a 2-liter Pepsi bottle contains 2 liters. If you pour it all into a pitcher, it's still 2 liters, but now it's the shape of the pitcher. A solid has a definite shape and a volume. Okay, a brick has a definite shape. It's shaped like a brick. And has a definite volume. In the gas, the particles are randomly arranged, disorganized, and far apart. Most of the gas is empty space. A liquid, they're randomly arranged, but close together. Like the subway, they slide past each other. A solid, the particles are fixed arrangement, very close. Particles are right there, they can hardly move. Density of a gas is low. Gas hardly weighs anything. A liquid is high, and a solid has a high density. Okay. Can you compress a gas? Yes. We do it all the time. Fire extinguishers are compressed CO2. People that have propane grills and that, gas in the tank is compressed. Because gas is mostly open space, we can move the particles closer together. What about a liquid? Can we compress a liquid? No. Which is a good thing because that's how hydraulic brakes in our car work. When we step on the pedal, the pressure from our foot is transferred to that little tiny brake line through the liquid all the way to the wheels, which push the pads against the rotors which stop the car. If you ever have a brake job done, your brakes fixed, the last thing they have to do is, anybody know? Bleed them. That means you have to take the air out. If you leave air in the brake lines, the air will compress, and you step on the pedal, and the pedal goes all the way to the floor, and your car doesn't stop. Well, it does eventually when you hit something, but it doesn't stop where you want it to. Okay? And you can't compress a solid. Now, someone was saying to me, yeah, I have a friend who takes his beer can and crushes it against his head. Well, that's an empty beer can, and what you're doing is compressing the air inside the can. If the can was completely full, you wouldn't do it more than once. Gas particles, moving very fast. Liquid, moderate movement. Solid, very slow. The interaction between the particles, the gas, essentially none. They're so far apart, they don't interact with each other. Strong with a liquid because they're next to each other. Very strong in a solid. So we're going to talk about intermolecular forces, boiling point, and melting point. Intermolecular forces are attractive forces that exist between molecules. So we have two molecules that kind of interact with each other. We're not talking about chemical bonds. Chemical bonds are intramolecular. So ionic bonds, covalent bonds, those are between atoms inside a molecule. We're talking about molecules being attracted to each other. We're going to talk about three different types of intermolecular forces. London dispersion forces, dipole-dipole interactions, and hydrogen bonding. The strength of these attractions determine what the boiling point and melting point of compounds are. To melt or boil a compound, you have to pull the molecules apart from each other. You're not changing the molecule, because remember, melting and boiling are physical changes. So if you have solid water, ice, okay, the water molecules, remember, are very solid, very close together, very strong interaction. Liquid, they're farther apart, so you have to pull the molecules. They're still water molecules, you're just pulling them apart from each other. So it becomes liquid. And when you boil them, you have to pull them even farther apart to become. become a gas. London dispersion forces. They're very weak interactions. Due to momentary changes in electron density in a molecule. This is kind of hard to understand. The change in electron density creates a temporary dipole. What is a dipole? If I were to take a magnet, at each end of the magnet we have a north and south pole. So how many poles do we have in a magnet? What's the prefix for 2? Dipole. So magnet is a dipole. Instead of north and south, we can think of plus and minus in terms of electron density. That's a dipole. Okay. What we have with London dispersion forces is a temporary dipole. All covalent compounds have London dispersion forces. The larger the molecule, the larger the attractive force and the stronger the intermolecular forces. So how can you induce a temporary dipole? The best example I could have is you have a tub of water and it's sitting on a table. It's nice and flat. You come along and you hit the side of it. What happens? It ripples, right? You get the little ripple thing in it. That's a temporary dipole, because if you go away and let it sit, it just smooths out again. Or if you drop a pebble in it, you get the little ripple thing go back and forth. That's a temporary dipole. When you do that, you kind of shift the electrons to one side, and create a partial negative and a partial positive, and after a while it all comes back. So all covalent compounds have London dispersion forces. And the larger they are, the larger the molecule, the stronger the forces. If we start with methane, methane at room temperature is what?
No gas.
Methane comes out of your furnace.
Yes.
Methane is not propane. Methane is methane.
Yes.
It's a gas. It's natural gas. Right? Propane is at room temperature. It's also a gas. But it has a higher boiling point than methane. So if we go up to hexane, hexane at room temperature is a liquid. Hexane's a liquid. Instead of hexane, if I said octane, octane at room temperature is a, where do we find octane? Gasoline. When you go to the pump, they have octane ratings?
Yes.
Yeah, that's because the octane is gasoline. So these, as we get bigger, those intermolecular forces get stronger. So their boiling points go up. When they're small, methane, propane, butane, which is cigarette lighters and that, they're a gas. Once you get above butane, you get pentane, hexane, octane, they become liquids. If you go even higher, eventually they'll become solids. So here's London dispersion forces between two methane molecules. So something happened to disturb it, like we hit the side of the water tub. So now we have partial positive, partial negative. So they're attracted to each other temporarily. Positive on one side is attracted to negative on the other side. So that's what holds the methane molecules closer to each other. But they're very weak. It doesn't take much to get them apart. That's why they're a gas at room temperature. Remember, temperature is a form of the higher the temperature, the temperature goes up, you feel hot. So temperature is a form of, thank you, heat's a form of energy. Okay, we're all coming back to the beginning part of the chapter on energy, okay? So room temperature, we have a certain amount of energy. For methane, the forces are so weak that the room temperature energy is sufficient to pull them apart, which is why they're a gas. When we get up to pentane, hexane, and octane, those attractive forces are much tighter. Room temperature, we can't pull them apart. They're a liquid. So to get those material into a gas, what do we have to do? Heat them up, raise the temperature. So their boiling point goes up. Gasoline. Or a component of gasoline. Now dipole. Remember when we did those molecular geometry and those shapes, and we have to figure out polarity. Formaldehyde, trigonal planar, we had a partial positive and partial negative. So once we got partial positive and partial negative, we have a dipole. So if I have two formaldehyde molecules, they're going to line up. A partial negative and a partial positive are going to be attracted to each other. These are stronger forces than London dispersion forces. Remember, the London dispersion forces were only temporary. Dipoles are permanent. They're always there. Formaldehyde, still a gas, much higher boiling point. Last of the forces are hydrogen bonds. Hydrogen bonds occur when a hydrogen atom is bonded to either oxygen, a nitrogen, or fluorine. So here we have an OH bond. I'll try to do it this way. Remember, water is a bent molecule. So the oxygen is a partial negative. The hydrogens have partial positives. So if another water molecule comes up, we just look at partial positive here. The dotted line symbolizes a hydrogen bond. It's not as strong as a regular covalent bond, but it's pretty strong. So we can have one here. We can have one here, and so forth. Anywhere an oxygen can be attracted to a hydrogen. Without hydrogen bonds, because you can imagine having the hydrogen bonds, stronger attraction between the molecules, the higher the boiling point. Water's boiling point is, this is where you chime in. Water boils at what? 100 degrees Celsius, T12 Fahrenheit. Without that, water would be a gas at room temperature. If water was a gas at room temperature, you wouldn't be sitting here listening to me, because I wouldn't be here, we wouldn't be here. Life wouldn't exist. Hydrogen bonds are very important bonds. Remember, hydrogen can also be attached to nitrogens. So in DNA has the staircase design, spiral staircase. The stairs are actually the nucleic acids. Purine, pyrimidine, purine. You can see between the oxygen and hydrogen, and between the hydrogen and the nitrogen, there's hydrogen bonds. That's what holds the staircase together. The stairs together. Okay? Now, if they were covalent bonds, we'd be stuck. DNA would be stuck. But since they're hydrogen bonds, we can actually break these bonds. And when we break these bonds, we unzip the DNA. So when we unzip the DNA, we then can come back with complementary nucleic acids and construct the opposite sides and end up with two DNA molecules that are the same. Okay? So we can reproduce. Again, a key to life. If DNA was covalently bonded in the middle, we couldn't unzip it, you'd be stuck. We couldn't synthesize proteins, there would be no translation, no transcription. Take an AMP, I'm sure you know all of that stuff by now. But it's all due to these hydrogen bonds. So, summarize. London dispersion forces, they're weak. All molecules, all covalent compounds have them. Dipole-dipole are moderate. So those are molecules with a net dipole, so polar molecules. Hydrogen bonding, strong molecules with hydrogen attached to either oxygen, nitrogen, or a fluorine. I'm looking at 3 here. If I give you these 3 molecules and ask you which one has the highest boiling point, we'd have to look at the intermolecular forces. Let's start with the weakest one, the London dispersion forces. Does this have London dispersion force? Okay, so this has London dispersion. Does this have London dispersion? Okay. Does this have London dispersion? Yes, all covalent molecules. So that was no help. Dipole-dipole. Is there a dipole-dipole here? Remember, carbon-hydrogen bonds are considered nonpolar. So there's no dipole-dipole here. How about here? Is there a dipole-dipole here? Yes, because we have a carbon double bonded to an oxygen. So we have, so this has a dipole-dipole interaction. What about here? Yeah, we still got a carbon to an oxygen. So this is a dipole-dipole. What about hydrogen bonding? First one, any hydrogen bonding? Is hydrogen attached to an oxygen, nitrogen, or fluorine? No. So, here, any hydrogen bonding? Is there hydrogen attached to an oxygen, nitrogen, or fluorine? No, so there's no hydrogen bonding here. How about here? Yes. So which one's going to have the highest boiling point? The last one. This is isopropyl alcohol, rubbing alcohol. This is acetone. And this is propane. So we know propane's a gas. We know acetone's a liquid. It's a nail polish remover, but it evaporates real quickly, so it has a fairly low boiling point. And then isopropyl alcohol. Oh, let's add one more here. H2O, London dispersion forces. Yeah, it's covalent. Dipole? Yes. Remember, water is bent. So we have actually two dipoles. So, hydrogen bonding? Oh yeah. In fact, we've got many fixes for hydrogen bonding. So actually, water in this case would be the highest boiling. Okay, that's how you would do it on a test. And you can tell this if you ever spill water on the table, and spill nail polish remover on the table, the nail polish remover will evaporate a lot quicker than the water because it has less intermolecular attraction. The boiling point is the temperature at which a liquid is converted to the gas. The melting point is when the solid is converted to a liquid. So again, the stronger the intermolecular forces, the higher the boiling point and melting point. Okay? So here, methane. Again, methane only has London dispersion forces. Its boiling point is minus 162 Celsius, and its melting point is minus 183. Water has London dispersion forces, dipole, and hydrogen bonding. Its boiling point is 100 degrees Celsius, and its melting point is 0 degrees Celsius. Big difference. Okay, any questions on that?
So that's all London forces. Is that the all London forces boiling point is negative 162?
No, just for that particular molecule. As the molecule gets bigger, the boiling points go up. So by the time you get the pentane, hexane, and that, they become liquids at room temperature. So here we have propane and butane. And you can see just by increasing it by 1 carbon unit, the boiling point goes from minus 42 to minus 0.5. So it goes up quite a bit. And so does the melting point. And actually, if you go up 1 more to pentane, it becomes a liquid at room temperature. Specific heat. That's the amount of heat energy in calories or joules needed to raise the temperature of 1 gram of substance by 1 degree C. We said that water's specific heat was 1 calorie per gram per degree C. It requires 1 calorie to heat 1 gram of water 1 degree Celsius. The larger the specific heat of a substance, the less its temperature will change when it absorbs a particular amount of energy. So the units for specific heat is either going to be calories or joules per gram per degree Celsius. If we look at some specific heats, here's water, liquid, which is 1 calorie per gram per degree C. If we come over here, aluminum, 0.2, copper, 0.09, iron, 0.107, much less than water. So they absorb heat less than water. Is that good or bad?
If
What do we use aluminum, copper, and iron for?
Potatoes, pots and pans.
Pots and pans. So if they had high specific heats, if they absorbed the energy, you wouldn't be able to cook anything.
More water, that's right.
They transfer the heat to whatever you're cooking, which is why they get hot. Okay?
Oh, I see. When you say it's a higher heat, it means it can hold more heat before it melts.
It holds more heat.
Before it
Don't say before it melts, it just holds more heat.
Okay.
So water has a high heat capacity, which is why people love to exercise in pools. Because when you exercise, you generate heat. If you're doing it outside, you just sweat. If you're in a pool, you're generating that heat. The water absorbs that heat, so you don't sweat as much, if at all. Okay, if you go into water that's at 50 degrees C, it'll absorb a lot of heat real quick. You can die of hypothermia. You hear about people all the time. You go, oh, well, you know, it's 70 degrees outside, you know, it's springtime, the ice has just melted, the water's at 40 or 50 degrees Celsius. They fall overboard. 5 minutes later, they're dead. The water just sucked all the heat out of their body. Silver has a low heat capacity too, so I guess you could cook in silver pots and pans. So how many calories are needed to heat a pot of 1,600 grams of water from 25 degrees to 100 degrees? I'm going to give you an equation. An equation, yes. The heat, which I'll call Q, is equal to the specific heat times the mass times the change in temperature. Okay. So here the specific heat of water is 1.00 calories per gram per degree C times the mass, which was 1,600 grams, times the change in temperature from 25 to 100 degrees. That change in temperature is 75 degrees C. So how much heat does that take? Takes 120,000 calories. Or 120 kilocalories, or 120 big calories. So it's a fairly easy calculation. Now every substance, as you saw, has its own specific heat. And they put it in scientific notation 1.2 times 10 to the 5th calories. Questions? Okay. So energy and phase changes. When energy is absorbed, the process is said to be endothermic. When energy is released, the process is said to be exothermic. Okay, when we do a phase change, the physical state of its substance is altered without changing its composition. So, let me ask you this question. We have an ice cube. So we have solid water go to liquid water. What do we call that? It's specific with phase change. Melting. To get ice to melt, you have to do what? Heat it. So you have to. So the ice is doing what? Absorbing heat or releasing heat? Absorbing heat. So ice is absorbing heat. Therefore, that's what kind of process? Endothermic. Now let's go back the other way. We're going to take the water, liquid water, change it to ice. So is that going to be an endothermic or exothermic reaction?
It requires energy. It requires energy.
I'm asking you.
What's the exothermic?
Exothermic releases energy. No, it is exothermic. So when you go from liquid water to ice, you release heat. That sound right? So you tell me if I take water, put it in an ice cube tray, for those of you who are younger people, refrigerators used to come with trays that you had to fill up with water and put in the freezer, and it turns from liquid to solid. I'm releasing heat, but the refrigerator, the freezer is what? Cold. I'm going to be releasing heat.
The apparatus that freezes the
Do you ever stand in front of your refrigerator?
heat of it.
What comes out from underneath?
Hot air.
Hot air. Where's that hot air coming from?
No? Come on.
It's coming from the freezing of the food. As it goes from liquid water to solid water, releases heat. The refrigerator takes that heat, removes it from the freezer compartment, and throws it out under your refrigerator. That's where all that heat is coming from. So freezing is an exothermic process. It has to be. You just told me melting an ice cube absorbs heat. Going the opposite way, it has to release heat. So if you've ever been, I'd say up north, it doesn't happen very seldom here, and the temperature is right around 32 degrees Fahrenheit, and it's miserable, and it's rainy, and it's gloomy, and it just makes you sick. And it goes just a little bit colder, and those raindrops turn into those big fluffy snowflakes. You could swear it's getting warmer outside. And it is. Because when it goes from those raindrops to the snowflakes, it's releasing heat. Melting is exothermic. Melting is endothermic, I'm sorry. It absorbs heat from the surroundings. Freezing is exothermic. It gives off heat. The amount of energy needed to melt 1 gram of a substance, remember we had specific heat. The amount of energy needed to melt 1 gram of substance is called the heat of fusion. So the heat of fusion of water is 79.7 calories per gram. So to melt 1 gram of water, you need 79.7 calories. When convert a liquid to a gas, that's called vaporization. Vaporization is endothermic. You have to add heat to boil something. Condensation, going back the other way, is exothermic. It gives off heat. Steam burns are probably one of the worst type of burn you can get. A steam burns twice. If you have a choice between 100 degrees Celsius hot water and 100 degrees Celsius steam, take the hot water. Because when steam condenses, it gives off heat. So you have that amount of heat on your skin. And then when it condenses, then you have 100-degree water on your skin, then you get burned a second time from the water. So if you've ever had a steam burn, I tend to get them routinely now that my wife works in the evening a lot. I'll come home for dinner and I'll put one of those things in the microwave with a little film on the top and put it in there for 4 or 5 minutes and take it out. I'll peel the film around, and what comes out, steam. It usually hits my thumb, and you get a blister almost immediately. The steam burns really fast. So liquid water, gaseous water, vaporization, endothermic. Condensation, exothermic. The amount of energy needed to vaporize 1 gram of a substance is called the heat of vaporization. For water, it's 540 calories per gram. Remember, to melt water, it was roughly 79 calories per gram. So it's almost 8 times more to boil water than it is to melt water. So that's why when steam condenses, it gives off a lot of heat. Sublimation is the conversion of solids directly to the gas phase. Sublimation is exothermic. So if you think of dry ice, that is solid carbon dioxide. If you put it on the table, it'll go directly to a gas. It doesn't go to a liquid. If there's any liquid on the table, that's water vapor that's condensed out of the air from the dry ice. Deposition is when the gas goes back to the solid phase. Deposition is exothermic. It gives off heat to the surroundings. Now, let's go back to our refrigerator. We filled up our ice cube tray with water. We put it in the freezer. And it's frozen. Now we have ice cubes. And we don't use them for about 6 months, for whatever reason. And we go and we look in the ice cube tray. What do the ice cubes look like?
You shrink a little bit.
They shrink a little bit. Where'd the water go? Because it's always been below freezing in the freezer. Where'd the water go? The what?
Condensate or evaporated?
Can't evaporate. Temperature's not high enough. What it does is sublimate. It goes from a solid directly to a gas. It never goes to a liquid. So, how do we know that's happening? In the old days, if you had a freezer, what would you have to do every so often to it?
Frost it. Chip it out.
Well, you'd open it up and the whole inside would be full of,
Ice.
where'd that ice come from? I mean, we just didn't make ice. We created ice out of nothing. It came from the ice cubes. It came from the water in the food. sublimates, comes to a gas, hits the side of the freezer, deposits, undergoes deposition, comes back out, and now the ice forms on the inside of your freezer. Today, you put food, you go and you buy meat or whatever, and you stick it in those food storage bags. You stick it in the freezer. You come back a month later with inside the bags ice crystals. That came from the water in your food. It froze and then it sublimated and it hit the inside of the bag. It came back out. So sublimation is an endothermic process. Deposition is an exothermic process. So we can actually construct a heating cooling curve. Right now, I'm going to, where's my little, I lost my little thing. Okay, we're going to talk about heating and cooling curves. A heating curve shows how the temperature of a substance plotted on the vertical axis changes and heat is added. So here we have, we're adding heat going this way. So this is the temperature. So let's say we start with ice. Let's could use this as an example. At minus 10 degrees C. Way below its freezing point. We start adding heat. So we're heating the ice. When we get to 0 degrees C, here we have a solid. We have solid ice at 0 degrees C. 0 degrees C, what does the ice start to do? Melt. So as it melts, we're going to have solid and liquid. The temperature doesn't change. It stays 0 degrees C until we get to all liquid. So now we have liquid water at 0 degrees C. Now we can start heating that water. So we heat the water and we get up to 100 degrees C. At 100 degrees C, we still have liquid water at 100 degrees C. It starts to boil. So we're going to have liquid and vapor or gas. As long as we have liquid water, it'll be 100 degrees C. Until we get all vapor at 100 degrees C, then we can heat the vapor. As long as we're doing a phase change, temperature is not going to change. So if you have, I go over this with my wife, if you have a glass of water, and there's water in there, and 2 ice cubes, it's 0. If you put 60 ice cubes in there, she always has to fill the glass all the way up with ice cubes. It's still 0. It doesn't make it any colder. It's like you got liquid water in.
You get colder faster the more you add to it.
Oh, I didn't say that. I said as long as you have ice and liquid in equilibrium, it'll be 0.
So don't it get colder faster if you add more ice to it?
It can, but you'll have less water too. But once it gets to 0, it doesn't matter if you add more ice. It's not going to make it any colder. Just like boiling water. If you have water on your stove and it's just barely boiling and the steam is coming off, that water is 100 degrees C. If you get it to a rolling boil, what they call a rolling boil, where it's bubbling up and everybody's dancing and that and the steam is just pouring out, it's still 100 degrees C. Yes?
Next question. So like when you're cooking, and say, well, I guess I make this certain type of ice where you have to mix water
sugar, and then you have to get it to a rollable, and then it turns into that, once it gets to a certain, like, the thermometer, it doesn't, like, it moves. Like, it goes up and up, like, I didn't think it would stop there, like, you can't let it get over a certain amount, because it could get.
Once you put something in the water, like sugar, you change the water's boiling point. We haven't talked about that yet.
Okay.
That's why you add salt when you're making pasta.
I'm not sure it has that much of a change effect on it. That little bit of salt you add, probably, but it does. We'll talk about raising the temperature. Sugar water will boil at a different temperature than plain water.
Okay.
Okay.
But it won't change its temperature, even if, like, the hottest your stove goes, and the water's a rollable when it's steaming, it's.
Because the sugar has, it's more molecules in it, so it has to go up higher.
Now when you
Well, I'm
have,
just talking about like water, like I would think it would just keep.
no, it doesn't get any hotter once it's boiling. Just like steam it, well, we'll talk about later, steam it just out in the air, it would only be 100 degrees C, whether it's just a little bit or a ton of steam, it's 100 degrees C. If you want to make steam hotter, you have to put it under pressure. When we get to gas laws, we'll talk about that. Cooling is just the opposite. We start with the gas, cool it down until it starts condensing. As long as we have vapor and liquid, it'll stay at the same temperature until we get to all liquid. Then we can cool the liquid. When it starts freezing, it'll stay at the same temperature until we get all solid, then we can cool it even more.
I mean, once it's a solid block of ice, it can actually get colder.
Yes.
Yeah.
Yes. If you go to the North Pole or Antarctica and you go outside, I'm sure that ice will be probably about -20, -30 degrees Celsius.
I've never 8 below zero. It went from freezing to 8 below with like 7, 8 hours. And with the wind, I couldn't tell a bit.
Wind chill is completely different.
Okay, it went from about 32 degrees a couple of days. It was record up in Alaska. It went from 30 degrees to 40 below.
Okay.
About 6 to 8 hours. Without the wind, it changed dramatically.
All right.
Without the wind, it was 40 below, but I couldn't.
You couldn't tell the difference between the ice?
No, it was cold.
I mean, cold is cold. I mean, you know, we only have certain ability. I mean,
But now metal's different. I know metal gets real brittle. Once it's hard when it's cold, but then.
I just say the physical properties of the ice change, it just gets colder.
Wow. I know that. No idea. No, I never thought of that. But I know metal gets brittle. It gets colder and colder, and you just bump it, it shatters.
So
Yes.
the colder something gets, the molecules don't get closer and closer together.
Only to a certain point. Well, when water freezes, it actually expands. It doesn't get closer. If you doubt that, go home and fill up small Pepsi bottles all the way with water. Stick it in the freezer. You put a beer, oh, okay.
And then freezer.
Yes.
So like in the winter time when you got like ice on your windshield, why do they say it's bad to like pour hot water on it?
Crack.
It's got nothing to do with the ice, it's got to do with the glass. And the glass will expand, and it's called thermal shock. If it expands too fast, it'll just shatter. In fact, what used to happen up north, most of you aren't northerners, Buffalo, you get a lot of salt on your car, people go through car washes, and you go through a car wash in the wintertime in January, and you come out, you know, hot water, people would come out, and all of a sudden it would be 10 degrees outside, their windshields would shatter.
You're from the north?
Yes.
So
You couldn't tell?
Is it toboggan a hat or something your eye?
It's a hat.
No, it isn't.
Toboggans are down
You're
here.
right.
Trying is something, you're right.
Toboggan, they used to say, put your toboggan hat on. People get that confused.
Okay.
But toboggan is not a hat. You're right.
So let's look at this example. How much energy is required to heat 25 grams of water from 25 degrees Celsius to a gas at its boiling point of 100 degrees C. The specific heat of water is 1 calorie per gram per degree C, and the heat of vaporization of water is 540 calories per gram. All right. First thing we're going to do is construct a heating curve that describes what we're doing. Not necessarily what we saw before. So I'm going to construct a cooling curve. So here I have my temperature. And here I have my heat. So I'm starting at what temperature? 25 Celsius, and we're starting as a liquid. Okay. So here I am, 25. I'm going to start over here so I can see it. As a liquid. What am I going to do? What am I heating? What am I doing? I'm heating it to. So I'm heating it to 100. I didn't say I was boiling it. That's correct. Oh yeah, I did. We're heating it to a gas, so we're going to go here to the gas part, because here we're still liquid. So I have how many steps? How many lines do I have? 2. Step 1, step 2. Step 1, I'm heating it 200 degrees. So how much energy? So I can say Q is equal to M times the specific heat times the change in temperature. How much water? 25 grams. Specific heat of water is 1.00 calories per degree C per gram. What's the change in temperature? 75. So if I do that, $18.75 calories. So that gives me step 1. Step 2, what am I doing? I'm taking the water and vaporizing it. So I need the heat. So this was step 1. Step 2, the energy for that is the heat of vaporization, how much energy it takes to vaporize, times the mass. So heat of vaporization is 540 calories per gram. It's calories. Times 25 grams. Q is the heat. 13,500 calories. So the total would be 15,375 calories.
You just add those.
Just add them up. And if you're going to do it to 3 significant figures, 15,300. No, 15,400, I'm sorry, 15,400. Does that go too, do I need to go back?
What was the heat of vaporization?
540. Can I extend it so it'll go up? Oh. Now you can't see it, right?
No.
Q is equal to heat of vaporization times the mass, which is 540 calories per gram times 25 grams is equal to 13,500 calories. Then I just added the two steps together. So that tells me how much heat I need to expend to get water from essentially room temperature to steam at 100 degrees C. Go ahead.
But the boiling point is 100 C, and then the vapor, to get it to vaporization, it's always going to be 540
For water, yes.
for water. The amount doesn't matter.
Yeah, because you put the amount right there in the mass.
Okay, so the more you have, the hotter,
No, the more you have, the more, it's not hotter, it's the more energy you have
the
to
more
put in.
energy that you have. Okay.
So obviously, if you have a pint of water and a gallon of water, it takes you longer to heat the gallon of water. It takes you more, but the final result for both boiling is 100 degrees C.
Vaporization is 540.
Yes. Per gram. So obviously, the more grams you have,
The same.
the more heat you have to put in.
How'd you get the bottom?
The 15,375, I added the other two. 13,500 plus
Oh, you added
1870.
together.
Yeah, plus the 1875. So you can see it takes a lot more energy to vaporize the water than it does just to raise the temperature. So a lot of times you've probably seen this when you're cooking. You got a pan on the stove with water, and you got the burner on high, and the water gets hotter and hotter and hotter. You know. But it's taking forever to boil. Well, number one, because you're watching it. You know, watch pot never boils. And number two is because it takes a lot more energy. Once you get it up to 100 degrees, it takes a lot more energy to get it to boil.
What if you added hot water into the, like, I was told that it would be the same amount, but if you added hot water, like, say your water temperature is 108, Fahrenheit, like, when you get it out the sink, and you put that in the pot, and you put it on the boil, and you turn it on high, is that going to heat quicker than, I was told that you still have to heat the pot and everything, still have to get down to the.
Well, if you ignore the transfer of heat from the pot, we're just talking about water. If you start with water, let's say instead of 25 degrees C, which would be room temperature, if you had the hot water from the sink, I'm guessing the hot water for sink at Celsius maybe 40 degrees. Then your delta T for the first one, instead of being 75, would be 55. So this part would be lower. But you can see this part right here, 1875 versus 13,500. It's not significant. So we're just going through the all right, they did it, they rounded everything off to 19,000 and 14,000. They came out with 16,000.
So are you gonna expect us to round those or just?
No. And this should be 1.00, not 1,000. So that's wrong right there. Basically, that's how you would do it. Questions? That is the end of chapter 4. So we did the whole chapter today. Okay.
Oh, we have a quiz on 4 or 4 and 5.
What do you mean we're having a quiz?
On this chapter, according to the Bible.
The test is on chapters 3, 4, and 5.